Hi, I'm Dr. Creasy. In this video, I'll show you how to expand your spreadsheet by adding 2 additional plies and building in the equations from Chapter 5 in Barbaro's textbook. I've loaded both spreadsheets into Excel, and so this is the first one that you've already completed, and then this is the new spreadsheet. So you can click this, hold Control, click the second ply, then let go of Control, right-click this, and select Move. You can either move it into the new book, the other book rather, or create a copy. So now we have 3 plies here. For the Module 3 assignment, you're going to complete the ply mechanics area on this sheet. If you look, you'll see these equations that have Chapter 5 equation numbers on them. If it's a Chapter 6 equation number, you'll wait until Module 4 before you complete that part of the spreadsheet. You'll notice here that I recommend using equation 5.18 to define the compliance matrix, and then you would just invert that to find the Q matrix. The equations for compliance matrix are very simple. Now all you have to do is invert it. If you haven't dealt with inversion equations in Excel, or matrix operator equations, you highlight the entire array that you want to create, and then you can press this is equal. Let's assume that, let me just delete this. So now I'm going to build this equation in. This is equal to the matrix inverse, and that just reminds you the name, you have to type the whole thing out, of what array. Now you just drag over this array, hit close parentheses. Now here's the trick. You have to hold down Control, then hold down Shift, then hit Enter. You can start working on these stress and strain transformation example problems. Fill those in, and that will give you experience in using Excel to solve homework problems and submit them. So for example 5.3, we want to transform those to the laminate coordinate system, where the x-axis is 55 degrees counterclockwise with respect to the lamina axis. So let's make a sketch to make sure we're doing these in the right directions. In this sketch, I show an element that's aligned with our x-axis right here. And we have to remember that fiber angles are measured for positive theta by moving counterclockwise from the x-axis, so off in this direction. So now, when the problem statement tells us that the fibers are in this position, saying that the x-axis is 55 degrees counterclockwise from the one direction, then we have to consider how are we going to define whether this is positive or negative. Well, one rule that I follow is if we're defining positive theta as counterclockwise, I would look at this angle to find theta. Now theta is positive. So my fibers would be at 180 degrees minus 55 degrees, since if I extend this line, the fiber here is 55 degrees away from 180. So in other words, I would use 125 degrees as the fiber angle. So now we get to look at example problem 5.5 again. We go to a table, and let's say that we pick a composite with this strength and these strengths in the fiber direction, the transverse direction, and the shear strength. These are all in megapascals. The strength ratio is, if I press F2, you can see that it's the available strength. So this is equal to that strength divided by the applied number. Hit enter, and that's a factor of 2. Now if I go Control D and copy these down, again, this is about 0, so the strength ratio is humongous. This is small. This strength ratio is large. The smallest strength ratio determines where this will fail. And this will fail at this strength ratio of 2. It will fail in tension in the fiber direction if someone should happen to double this state of stress. And now we say, what happens if we made a mistake and this is actually minus 200? Just on hitting enter, you can see the state of stress changes. Now notice there's tension in the fiber direction, but there's almost twice as much tension in the transverse direction. There's also a significant shear stress. Putting all the fibers at 26.57 degrees under this condition is a terrible mistake. So again, this automatically updated. We still have almost 6 times the strength needed in the fiber direction, but we only have 12% of the strength needed in the transverse direction. So if we took these stresses and said this is equal to that divided by 20, we could then just put the values in there, and you would see that now we've got a safety factor of 2.5. And so this component would probably be acceptable, but it's made much thicker because the fibers are not oriented in an optimum way. They're oriented in a weak way.